Is the screen visible now?
Yes, sir.
Yes. Fine. Good morning. So let us begin the class for the today. So yesterday we have seen some of the problems, and we'll continue with programming of examples of SIC, SIC, So hope you have a clarity about what you discussed in the previous class. So today's agenda is, if you have any doubts on SIC addressing modes, we can quickly recall. At 8:45 we have a quiz. You will get a quiz at 8:45. Maybe in 5-10 minutes you can finish that. Once you are done with that, we'll come back to the programming examples. So before that, let me give an idea how we can write a program in assembly language. So hope some of you would have written some programs of assembly language at your undergraduate level, but nothing to worry. Let us learn from the beginning here. So assembly language program is like any other language program, like your high level language, C, C++. The only difference is you may not be having a very structured or day-to-day life type of printf, scanf, cnco type of statements, but we'll have a medium level like add, sub, LTA, LDA, STA, which will give a meaning of what action we are going to take place. But nevertheless, there are also instructions like your printf and scanf, which are going to be used, but that may not be that structured as we see in our high-level languages, but still we can write a program using assembly language constructs. So before we indulge in writing a program in assembly language, we should know some of the directives, which are called as a assembler directives. Hope you might have studied some of these directives at your CO level, where teacher would have discussed about start, end, origin, data word, reserve. These are some 5 or 6 assembler directives that was there in the syllabus. If you remember that, that's what the concept of a assembler directive we are discussing now. But nothing to worry. As we know, each architecture is unique, and assembler directives also will be varying from architecture to architecture. But what is remaining constant here is the concept of assembler directives. So as the name says, assembler directives, directive like your preprocessor. Directive means they are going to inform the assembler that this is the action what we have to take when those values are assembled or those values are used in the programming. For example, when I say start, start, what is the information I am giving to the system or assembler that this is the beginning of my program, like your main statement in your C or C++. Similarly, when I close the brace, we say that it is the end of the block or end of the program. Similarly, I can use E and D, which denotes that this is a end of the program. So like that, we have a various directives. Even in discussion of SS, we'll be discussing around 20 assembler directives as we go now onwards. But today, let us give the 3 to 4 directives which we'll be using in our module 1 programming. So those directives, as the name says, assembler directives can be defined such that these are the directives or information to the assembler what action they need to take during the assembly of the program. They are only informators. They are like a traffic police for you. For example, you are traveling from one place to another place. Let us say you're traveling from Bangalore to Bombay. You are at Tumkur now. So from Tumkur, there are 2-3 directions. How to go to Bombay? If you don't take proper direction, you may end up in joining Hassan or Kunigal, or you may go to somewhere else, or you may not go to Bombay. So when you stand near the circle of Tumkur, there will be 3 directions, which will lead to 3 different places. You are going to choose the place what you want to go. That is the directive. So the signal will never join you during the journey. Signal will remain there itself. Similarly, your assembler directives are those which are only informing the programmer or the assembly or assembler that what action we need to take now onwards, but they will not participate in the object program. So one thing what we have to remember in assembler directives is they are like any informative what is a contribution to the assembler, wherein they only guide the assembly of the program, but they never participate in the assembly of the program or in the object program of the program. So that's what we have to keep in mind. They are only a placeholders. They just guide what action we need to take now onwards, whether to stop or end or what type of action we can do with respect to the further program of a assembly language, but they will never participate in the object code. We'll discuss more on that, but right now we can keep this in mind. 2 points at this juncture. Assembler directives are a notional representation in the course of assembly program which guide the how the assembler should be looking at the program whenever those assembly directives are used. Second, they will not participate in the object program creation. That is the concept what you have to keep in mind at this point of time. So coming to the assembler directives that we are going to use today, there are 4 directives. One is RESB, RESW, BYT, byte, WORD, word. These are the 4 assembler directives what we'll be using today in our program. So what RESB stands for? As the name says, reserve 1 byte of data. RESB stands that it is like a int A, int B. Whenever you use in high level language, you will be using int A, int B, where or character A, character B, where you want to create a place so that I can add some data into A or B. Similarly, RESB is similar to creation of a variables like characters, integer, float. But in this case, since it is 1 byte is nothing but a character. Similarly, RESW, reserve word. I'm going to create an integer type of data because we know that in SIC, an integer takes 1 word. That means 3 bytes. Thereby, when I say RESB, I'm going to reserve a character. When I say RESW, I'm going to reserve an integer. Similarly, in high-level language, we have a char and integer. That is what we can understand. Next, we have 2 more called byte and word. So byte says it is a constant. You also have in high level language constant int A, constant int B, constant character A, constant character B. You know the difference between variable and a constant, right? The same concept, byte and word we have. So byte represents creation of a constant, which is a character constant. Similarly, word represents creation of a constant, which can be used for an integer purpose. So this is what the 4 assembler directives, what you need to keep in mind. So any clarity required here? The 4 assembly directives. Able to understand?
Yes, sir.
Fine. Next. Okay, having said that, we have assembly directives. Now we should know how to write a program. So for every language, we have a format. In high level languages, if we say C, we say we will have a header files, followed by your pre-processed directives, followed by global variables, followed by main program, followed by user-defined function. Similarly, C++, we have a pretty same. If you go to COBOL, I don't know how many have heard about COBOL language. COBOL has a very peculiar format where every character position matters, 0 to 6, comments, 7, some numbers, 8 to 73, program like that. Every character counts like that. Every language has its own format. Similarly, assembly language in general, I'm talking about in general, assembly language in general has a format while writing the program. The typical format is like this. We have a 5 column. One is a machine address, second one is a label, third one is an opcode, fourth one is operand, and last one is the comments. So this is how a good programmer, a professional programmer of assembly language will be able to write a program. If you write a program in this format, that is globally accepted. It is a convention as well as it is how people are going to follow. So first one is a machine address, second one is a label, third one is a opcode, fourth one is operand, fifth one is a comments. So what is a machine address? We know that memory cannot be directly handled by the user. We can only write the program, submit to the system. System will be loading wherever the memory is available at a given point of time. But in assembly language, we have a small flexibility wherein we can communicate to the system that, okay, no doubt, I don't have a flexibility of informing the system that my program should start from a location, but still I can specify. If I specify that, system will be looking for that particular address if it is free. If it is not free, it will store at the available location. So it is not mandatory, of course, because we cannot mandate the system that my program should always start from this location. Not possible. However, you can specify as a programmer, if that address is available, that will be considered. If it is not available, system will be loading the program in some other location that we call as a relocation of the program. We'll discuss that in detail later. But right now, we know that in assembly language, there is a small flexibility for the programmer to inform the system that my program may be used or may be loaded from a location, let us say 8000. 6,000, 2,000, 5,000. You can specify any number of your choice within the boundary. If it is SIC, 0 to 32 kilo. If it is SICXE, 0 to 1 MB, because these are the address names. That's how we can use, not beyond that. Any number within that range you can use for your convenience. Normally we use 8,000 because we have been talking about Intel processors, 8-bit like that. So 8,000 is typically used by any assembly language, or even if you refer books, you will get better. There is no rule that you should use 8,000 only. As I said, we have flexibility from 0 to 32K in SIC, from 0 to 1 MB in the place of a SICXE. But some address between that range you can use. Just to give an understanding of you, I've just used 8,000 something. Next, label. Label is like your, let us say, you might have used it in C language, go to statements. Go to. Go to means I can say from, normally go to is not a recommended way of program in C or C++, but still we can write a go to statement so that I can go from one location to another location. That is an impractical way, but imagine a kind of situation like that where I can jump, branch from one location to another location. That is possible using a labels. And third one is the opcode. We have seen yesterday also two of examples, LDA #3 plus JSUB RDREC. So that is what the first beginning, ADD, LDA, STA, which represent our opcode, followed by operand. So opcode, operand should go together, because when I say ADD, on which I'm going to perform ADD. That means addition operation I am performing on something. What is that something? Is through represented through the operand. So whenever we have an opcode, opcode will always follow the operand. So ADD something, LDA something, STA something. The last column is the comments. Even in high level language program, it is advised that we write comments just to understand that how the program is being run. So that comments what you write in high level language is similar to the comments what we are going to talk about here in assembly language program also, though, so that when you go back to the program after some time, you yourself might forget why I have written this instruction. So better to write a comment so that whenever you refer that, you'll be able to understand easily. So this is the format of a assembly language program in general. What is that? Mission address, label, opcode, operand, comment. But all these five are not mandatory. If you want to write, you write. That is a good way of writing. But you cannot write in day-to-day activities or in your examination and all. Probably then we'll go to the which is important or which is mandatory, which is not mandatory. So in this assembly language format, opcode and operands are mandatory. As I said, you are performing actual programming like add, LDA, STA, that is opcode followed by operand. So opcode and operands are mandatory for us, whereas label is optional, meaning that if you are using a branching, you may have to use label. Otherwise, you may not use the label. So comments, of course, is left to you. If you want to write comment writing is a good practice, but it is left to the programmer. If programmer is well versed with the program or whatever he or she is writing, comments are not required. Or if you're writing a program for somebody else, then probably comments you may need to add so that the other person can understand your logic behind the program. Otherwise, opcode and operand or minimum one should be writing in any assembly language. Machine address is required while assembly. Otherwise, while writing the small program and source program, machine address is not mandatory. But when you start assembling the program manually later for the assembler point of view, then the machine address column is required. Otherwise, when you start writing a program per se in assembly language, opcode, operand, minimum required. Next, if you're using a label you may have to use. Otherwise, this typical format of opcode operand is sufficient for writing the assembly language program. So this is the format. We'll take up some of the programs. Before that, you might have received a quiz now, so you can complete the quiz. Meanwhile, I will take the attendance. Hope you all received the quiz. Have received?
No, sir.
No. Okay. Let me check once again. How about now? Have received it now?
No, sir.
No, sir. No, sir.
Just refresh your mailbox.
We got, sir.
Got no? Just check, refresh, and you should be able to get. So try to complete in 5 minutes. You need not take much time on that. Meanwhile, let me go through the attendance. So Asta,
Present, sir.
Abhinav,
Present, sir.
Aishwarya,
Present, sir.
Ambarish,
Yes, sir.
Anu.
Present, sir.
In voice ಇಲ್ಲ ಅನು
Present, sir.
ನಿದ್ದೆ ಮಾಡ್ತಿದ್ಯಾ?
No, sir.
Okay. Arbaz, Arbaz, Arjun,
Present, sir.
Ashok,
Present, sir.
Vinita,
Present, sir.
Bhargavi,
Yes, sir.
Bhavisha,
Present, sir.
Chaitra,
Present, sir.
Chatterjee,
Present, sir.
Diksha,
Present, sir.
Deepika LG,
Present, sir.
Deepika MB,
Present, sir.
Murali Krishna,
Present, sir.
Gangubai,
Present, sir.
Guriya Kumari, Harshit,
Present, sir.
Junjar,
Present, sir.
Kavya,
Present, sir.
Kishore, Lata,
Yes, sir.
Manisha, Manjunath.
Yes, sir.
Present, sir. Mani.
Okay. Nayana,
Yes, sir.
ವಾಯ್ಸ್ ಇಲ್ಲ ನಯನ, ಜೋರಾಗಿ ಮಾತಾಡ. ಗುಡ್. ನೀಲಾಂಜನ್, ನಿಶಾಂತ್,
Present, sir.
ನಿಶಾಂತ್.
Present, sir.
ಓಕೆ. ಪವಿತ್ರ,
Present, sir.
ಮೈಥಿಲಿ,
Present, sir.
ಪ್ರಿಯಾಂಕಾ,
Present, sir.
ಪವನ್ ಕುಮಾರ್, ಆಕಾಶ್,
Present, sir.
ರಾಜೇಶ್ವರಿ,
Present, sir.
ರಾಕೇಶ್,
Yes, sir.
ರಮ್ಯಾ,
Present, sir.
ರಶ್ಮಿ,
Sir, present.
ರವಿಶಂಕರ್,
Yes, sir.
ರಿಜ್ವಾನ್,
Present, sir.
ವಿಶಾಲ್,
Present, sir.
ಸವಿತಾ, ಶ್ರುತಿ,
Present, sir.
ಸ್ನೇಹ.
Yes, sir. Savita, present.
ಓಕೆ ಓಕೆ. ಸ್ಫೂರ್ತಿ,
Present, sir.
ಶ್ರೀನಿಧಿ, ಶ್ರೀನಿವಾಸ್,
Present, sir.
ಸುನೀಲ್.
Present.
ಓಕೆ. ಸುನೀಲ್,
Present, sir.
ವೈಷ್ಣವಿ,
Present, sir.
ವಿನಿ.
Present, sir.
Arbaz is
Fine.
present, sir.
ಓಕೆ ಅರ್ಬಾದ್. ಹೌ ಅಬೌಟ್ ಗುರಿಯಾ, ಕಿಶೋರ್, ನೀಲಾಂಜನ್, ಪವನ್ ಕುಮಾರ್.
Yes, sir.
ಗುರಿಯಾ.
Yes, sir.
Okay. So let me know once you're done so that we can continue with the class. Those who have completed, you can copy this information. Already we have taken yesterday 2 things. That is a hash for immediate addressing, plus for format 4, and 2 more we can take today. That is @ symbol for indirect addressing. And don't take the star right now. You can skip the star. Take the last one. C followed by 2 single quotes. C followed by 2 single quotes represents character string. These 4 we will be using. The star we'll use later, but right now don't worry about star. So hash @ plus C followed by 2 single quotes. Hope the screen is visible to you.
Yes, sir.
Okay, fine. Next. So let us get into the programming examples. Again, in the examination, they will ask you, write a program to perform this, write a program to perform that. Okay. So we should be able to write programs for sample or typical, 4 types of requirements. Probably I can recall your attention to CO again, where you might have studied about different types of what you call activities that a particular program will be able to do. The type of data transfer what we have between various instructions, or various locations, maybe the arithmetic type of instructions, the basic type of instructions. What you have seen is a basic addressing, for example, 0 address, 1 address, 2 address, 3 address. Similarly, we have various instruction types as far as the various performance of data type as far as the architecture is concerned. They can be data transfer. Second, they can be arithmetic operations. Third, they can be branching and looping. And fourth one is a IO. Similar to that, all these 4 categories we'll see from SIC, XC point of view. The 4 varieties of instructions we can look at, or types of instructions we can look at from the data movement point of view, or maybe computational point of view. They are nothing but data transfer between memory and register, or register memory, or vice versa. Next, we have arithmetic logic operations. Next, we have a branching and looping operations. Next, we have input and output operation. These are the, from operation side point of view, how the instructions can be categorized. One way of categorizing instruction is based on the address. 0 address, 1 address, 2 address, 3 address. The other way is based on the type of operation they perform. We can transfer the instructions into 4 types. One is a data transfer instruction, arithmetic logic operation instructions, branching and looping instructions, and input and output instructions. What we are seeing here is now that 4 categories like data transfer, arithmetic, branching and looping, and input output. So are you ready to go for the examples? If quiz is over, I can take these examples. Okay, so let us take the first example. Data transfer in SIC. Data transfer in SIC. That is the first level we'll see. We'll take this under both SIC as well as SIC XC. Data transfer in SIC. To recall the architecture of SIC, there are only 2 data available in SIC. One is a character data, other one is a integer data. If at all any data transfer has to take place in SIC, that can be with integer or character, not anything else. But if with SIC XC, it can be character, integer, floating point. Since we are in SIC, we can only think of either character or a integer. And we also know that SIC is a very simple architecture compared to SICXE. Its flexibility is very less compared to again SICXE. So before writing a program, what you should be keeping in mind, your architecture of SIC you have to keep in mind. What is architecture? How many registers are there? What is the memory? What type of data in formats we have? What type of instructions? They should come like a picture in front of you. Then only it is going to be easy for you. Maybe initially let us recall one by one as and when we go. But otherwise, as you want to become a good programmer of assembly language, your architecture should be there in the backside of your memory. Then only it is easy for us to write the program. Otherwise, you have to refer the manual every time. So I want you to keep what you call your instruction set that I have shared yesterday with you, so that easy for you to understand whatever instruction I'm using are there in the SIC instruction set or not. Hope you have that PDF what I have shared yesterday with you, that instruction set. You can keep that open. Yes. So what is the requirement here? Data transfer. What do you mean by data transfer? Or what are the ways data transfer can happen? So where is the data now? Data is in the secondary memory. When data is in the secondary memory, I can transfer the data in the secondary memory itself from one location to another location. Second, from secondary memory, I can transfer the data to your processor registers. Third, from processor registers, I can load the data or transfer the data to memory. So data transfer happens in three ways. One, memory to memory, memory to register, register to memory. So registers are there in the part of the processor, so memory is away from it. That's what we discussed about the CO first chapter. Input, memory, processor, output, that relationship diagram. So if you get that in mind, so memory and processor are away to each other. They need to be connected well so that the data transfer happens. So data transfer means transfer of data within the memory from one location to another location, which you call it as a memory to memory data transfer. Or data transfer can happen from memory to register of the processor, or data transfer can also happen from register of the processor to memory. So these are the three ways we can look at the data transfer. Here we have typically written some data that is moving from one location to register and back to memory. So that's what the concept here is. So LDA 5. So what is LDA? We have used the same instruction yesterday also. If you refer that instruction set, somewhere we see LDA. In the last column, they would have written some information. Right now, it is not understood by you. Nothing to worry. But otherwise, LDA stands for load into the accumulator. Load into the accumulator. That means we are loading some value into the accumulator. When I can load value into the accumulator, it should be either in memory or it should be in the another location. I mean another register. So if it is another register, I cannot use LDA. So LDA means always loading from memory to register. So LDA always stands for loading a data which is existing in memory to the register, because accumulator where it is existing in the processor. So LDA stands for loading the data from memory to accumulator. So that's the concept of it. So what data I'm going to load? LDA is a opcode, FIVE5 is a operand. Just now we have seen the format of a assembly language where every opcode should follow the operand depending upon type of instruction what we have. If it is a format 1, format 2, format 3, format 4, like that. Since it is SIC, there is only one format. There is no extra format. There is only one format, which is a 3-byte format. So LDA5 means I am loading a data from memory to accumulator. So where is the memory now? Where is the data? Data is in the location called as a FIVE. So FIVE here is a address of the operand. It may look like a number, name for us. It is a name like int A, int B, int C for us, where the data will be stored at int A, int B, int C, ABC location. Similar to that, we have 5. We can write anything. We can write any number here. It is like your data type here. So LDA 5. So 5 means 5 is the name of the location at which some data I have stored. The data can be anything. Since 5 is being used here, I say there is a number 5 stored at the location F5VE. So what is F5VE here? F5VE is the address of the location, depending upon the type of addressing we have. In SIC, there is only 2 address. One is the direct address, other one is the index address. There is no index X being used here, so it is nothing but a direct addressing. So LDA 5, the one statement has so much of discussion. What is the discussion? It is going to load the data from memory to accumulator. It involves direct addressing. The data that is stored in the location FIVE is going to be considered and loaded into the accumulator. This is what the meaning of the simple line called as a LDA 5. So any doubts here? The first line?
No, sir.
Fine. Now what we have done? We have transferred the data from memory to register. Now what I will do now? From register, I will transfer the data back to memory. So after LDA5, what happened now? The data what is there in memory now has come to the processor and it is sitting in the accumulator. So from accumulator, I will transfer the data back to memory. For that purpose, I have a STA. STA means store from the accumulator. Store from, that means take the data from accumulator, store somewhere else. Since similar to LDA, LDA means memory to accumulator, STA means accumulator to memory. So when I take the data from accumulator, I can only store into the either one of the registers or into memory. But STA is not going to store the data in another register. It will always store back in the memory. So LDA, STA are the complement to each other. So LDA takes the data from memory, stores into accumulator, whereas STA performs the actually reverse direction. That means takes the data from accumulator, stores back into the memory. So whatever the data I have stored in accumulator, what is the data I have stored in accumulator? Some data, let us say 5. That 5 is going back to the memory to place called as a LOC. I have created a variable by name LOC, which is going to be stored or which is going to be used rather to store the data that I am taking from the accumulator. At this point of time, accumulator contains value 5. That value is loaded at the location LOC. That's what we have written on the top. But how does the system know what is FIVE, what is LOC? Then we have to inform that whether it is RESB, whether it is RESW, whether it is a word, whether it is a byte, that information we have to give. That's what we have defined here now. So FIVE, LOC, that two should be written at the label column. So FIVE, LOC should be there in the label column. Word and RESW should be under the LDA, STA, that is opcode column, and 5 and 1 should be at the part of the operand column. So here you can see 5 and LOC are going to be labels. Just now we have seen the format. The format says we have a label, opcode, operand, comments. We said that opcode and operands are mandatory, whereas a label is optional. Now I have used label by name FIVE, LOC. They will be in the first column called as a label. Next LDA, STA, WORD, RESW, they all come in the column called as a opcode. And FIVE, LOC, number 5, 1, they will come under the concept of a operand. That's what you should be writing when you write the program. So that completes the program. So one program. What we are doing now, we have taken the value 5. That 5 is loaded into accumulator. Later, from the accumulator, that value 5 is loaded back to the location called as a LOC. Now let us see why we have used word, why not byte, why we have used RESW, why not RESB. Let us see now. So 5 is the location name, like int A, int B, int C. In int A, int B, int C, I can load any value. Similarly, in integer value for that matter. Similarly, FIVE location, I want to load an integer value. So integer can be represented using either word or resw. But what type of integer I want to do now? It is a constant integer 5 I want to load. So I need to have a word. I'm not going to create a variable. I want to create a constant. So we have used word because it is an integer. If it is a character, I could have used byte, but I want an integer, so I have used word. Similarly, when I want to store an integer back at some other location, I should have the enough memory. So integer takes how much? Integer takes 1 word or a 3 bytes. So when I'm storing a data back to some location, that location should be compatible enough to store the data what I'm transferring. When I'm transferring an integer data, my location should be capable enough to store the integer. When I'm storing a character data, my location should be capable enough to store the character data. So depending upon the length or size of the data that is under transmission or a transfer, the location or the placeholder should also have the similar size. Otherwise, you will get a underflow or overflow or memory mismatch problem. So since I'm transferring a 1 word data, I should also reserve 1 word memory. If it is a 1 byte data, I could have reserved 1 byte. Since I'm transferring a word here, I'm reserving a 1 word data. So LOC RESW 1 means 1 word of memory, that is 3 bytes I am reserving. Why 3 bytes? Because my value 5 is an integer which is also of the size 1 word, and hence to load that value 5 into a location, I should have the location that is also equal to the size of my data, which is a word, and hence we are reserving the word of data. So that is the first program what we have as far as the data transfer is concerned. So let me know any doubts you have at this point of time. Is it clear?
Yes, sir.
Fine. So now we have transferred the data, which is an integer type. Let me take another program where I will transfer a character so that you will see the difference between transferring of a data of an integer type or a character type. Just recall now here, I have a LDA, I have STA. Okay, now let us see. So here the question is how to transfer the data, which is a character from same process, memory to accumulator, accumulator to memory. So I again want you to go to the instruction set and observe instructions by name LDCH and STCH. Look for the instructions by name LDCH and STCH. Let me know whether they are available or not, because I can't use an instruction here which is not there in the list what we have with you. I should be using only those. This was your language, assembly language, characters. I cannot use anything other than that. So confirm me if I have LDCH and STCH in your sheet.
Yes, sir, it is available.
So that means when you write a program, you should be using only those instructions which are available under the particular architecture. If I am using a Pentium 1, I should be using only those instructions that are supported by Pentium 1. Since I am using SIC, I can use only those instructions which are available in SIC. Now I want to transfer the data, which is a character. Just now we have transferred the data, which is an integer, for which I have used a LDA, STA. So system clearly knows if I use LDA, I am transferring a word of data. If I am using STA, I am also transferring a word of data. But now the requirement is a character data transfer. So LDCH stands for, as the name says CH, we are going to transfer a character data, which is a 1 byte. Similarly, STCH means again 1 character of data is being transferred. The process remains same. So LDCH means instead of LDA, we have LDCH. In LDA, what was the meaning? The data from memory is loaded into the accumulator. Same concept here. The data from memory is loaded into accumulator, but only difference with the LDCH is that it is not an integer here, but it is the character. A character constant like C, A, X, Y, 0, 1, any character for that matter can be loaded from memory into accumulator using LDCH. I'm retaining the same FIVE, that is the name of the constant, which is a character here, which is some value, some character. Similarly, that value which is loaded in the accumulator is written back to the memory using the STCH. So STCH always takes the data which is a character length from accumulator and loads back into the memory. So when you're loading back into the memory, memory should have a assigned location name, and you should also have a capability to store. Since the character takes 1 byte, I need to reserve 1 byte of data. That is the reason why LOC is reserved with 1 byte. See the difference. In the previous example, it was RESW because it was an integer. Now it is RESB because it is only a 1 single byte we want to transfer. Similarly, your attention is required here. 5 byte. In the previous example, you have written 5 word and number 5. Now I am just transferring what? A character constant. That's what we mentioned here. The special symbols. We have used the special symbol C followed by single quotes for which one? For a character string or a character constant. So when you are using character string or character constant, we need to write C followed by 2 colons. Similarly, since we are talking about a character transfer from main memory to accumulator or accumulator to main memory, whatever the case, we need to represent that in a character constant. So for that purpose, we have a 5 byte C within single quotes 5. Suppose you want to transfer Z as a character. So what I should be doing now? I will replace 5 with the Z. I want to transfer M as the character. What we'll do now? I will replace 5 by M. Like that, whatever the character you want to transfer, that character need to be kept in single quotes, prefix it with the C. Then we mean that it is a character constant, not the number. Otherwise, it may take it as a number or something else. System might get confused. To avoid that confusion, we have to prefix with the C, telling it is a character, and keeping that in single quote says it is a character constant, so that internally a proper ASCII code will be generated for the system. So this is a program for the data transfer of a character from either memory to processor or from processor to memory. So this is the first example of data transfer as far as the SIC is concerned. So let me know any doubts till this point. Any confusion, any doubt, any missing clarity? No doubts?
Sir, I explained about it 5 byte that once.
Pardon?
5 byte.
5 byte. Okay. See, you understood the previous one, 5 word?
Yes, sir.
Now, why we are writing 5 word here? 5 is the name, like int A, int B, int C. Word is because it is an integer that we are going to transfer. But in current example, 5 is a name like character C, character A. You declare no, char A, char B, char C. That char is nothing but your byte. ABC is nothing but your 5. I've written 5 because there is a name of the character variable, a character constant in this case, because I'm using a byte. So byte will be 1 byte. If it is a word, 3 bytes. That's all the difference. So character always takes a 1 byte. If it is an integer, I could have used word as we did in the previous program. So now it is a character, I'm writing a byte. Is it clear?
Yes, sir.
Okay. So if you don't have any doubts, next question is data transfer in SIC XC. This is one architecture. We'll see another architecture. You will appreciate the difference between these two architectures in making the program easier or compact. So data transfer in SIC XC. So whatever the programs I have written now, data transfer of an integer, data transfer of a character, we'll write the same programs, but using SIC XC, you will appreciate the differences. Same program, same performance, but you will see the difference in the efficiency of the program. So data transfer using SICXE. I will show here. You just read it. Let me know if you have any confusion. This is the solution for that data transfer in SICXE. So I will recall your attention to these special symbols. So use them if they are used anywhere. So this is what the program. First one is the program for the SIC data transfer of integer. Second one is the program for SIC data transfer of a character. But in SICXE here. Do you see any differences first? Changes? Same program, no change. But architecture is different. SIC is the lower version. SICXE is the advanced version. So when you go to advanced version, what is happening in the program? What are the observations you see here? Which is easy to read first? Previous program or this program?
This one, sir.
So data transfer in SICXE program is easy to read. Agree?
Yes, sir.
Second, what is the number of instructions you have written earlier?
4.
4. How many now?
3.
So that means as you grow to the advanced version of architecture, which has an inbuilt complexity, who is advantageous now? Programmer is getting advantages. Agree? Because my effort are less. I'm able to write a better program, good program, readable program with less effort. So as the complexity increases in the architecture, it is good for the programmer. That's what you should be writing when there is RISC, CISC. You might have written, if you have already written the assignment, the difference between RISC, CISC is the programs in RISC look bigger. Just now we have seen 4 instructions of SIC has become 3 instructions. So 4 instructions is more than 3. That means 25% of code is reduced in this program. That means your RISC programs always look bigger in size, whereas your CISC programs look compact in size. Second, your RISC programs are not that easy to understand readability point of view, whereas your CISC programs are easy to understand or provide the greater readability. This is how we have to slightly differentiate between RISC and CISC. Second, why it is so important or why it is so easy in SICXE? Because SICXE has a more complexity internally. That complexity is helping us as a programmer or user to write a better programs. Whereas in SIC, there is no complexity. Since there is no complexity in the architecture, no complexity comes in writing the program, because you will be writing a bigger program for a smaller activity. Whereas in the case of SICXE, you are writing a very, very small program, even if it is a big activity or a big program. That is the beauty of the CISC type of architectures. But the problem is internally architecture design is very, very, very complex. That is what you have to understand. Now let us see meaning of this now. So LDA, you know, LDA means I am loading the same data that is in memory to accumulator. So in the previous example, we have used LDA5 because I never had a immediate addressing there. But here I have an immediate addressing. I will directly store the value into accumulator by writing the immediate addressing. I need not go to your location now. I will directly transfer the data 5 into the accumulator. So this is possible because I have a immediate addressing mode. Whereas in SIC, there is only 2, direct or index. There is no immediate addressing mode, and hence I could not transfer the data into the accumulator. Similarly, STALOC, whatever the data I have in memory, I'm storing back to the, whatever data I have in accumulator, I'm storing back to the memory location. It is same as that, there is no change. Second, since I have not created a location for the number 5, I need not write that again. If you remember the previous example, we have written 5 word 5 because that word has to be loaded somewhere, because the value 5 need to be stored. But here, since we have already used immediate addressing, that particular requirement is reduced and you can directly go for a LOC RESW. That is the concept. Similarly, the other program, LDCH number 5. So when I say LDCH 5, immediate addressing, I am storing 5. Here that business of byte, C, colon, all this not required. It's very, very simple for us. I can say since CH stands for a character, I am loading a character which is a 5 into accumulator. As simple as that. So that's how the higher advanced architectures will reduce the effort of the programmer in writing a better and bigger programs. That is the advantage of a CASE type of architect. This is just one part of the, so data transfer instructions are programmed in both SIC and SICXE, and you will appreciate the advancement of technology or the architecture in SICXE, which will give a flexibility for the programmer to write a better programs. We'll see the remaining. There is arithmetic operations, branching data operations, and IO in the next classes. So if you have any doubts till that, you can let me know. Otherwise, we can conclude the today's class. Any doubts till that? Data transfer?